Hello, I'm Susan Nash, AAPG. Delighted to welcome you tonight to week 12, Pivoting During the Pandemic. Theme tonight is Sustainable Solutions for the Energy Transition. We have a great group tonight, starting with Miriam Winsten, Mangrum Hill, Edith Newton Wilson, Rock Whisperer, Cynthia.Dacre, Maxar, Anna D'Alessio, Ivaldi Group. And then we also have our faithful friend, Larry Davis, who's a professor of economics at Texas A&M Texarkana. So I'd like to invite Larry to say a few words.
Well, just welcome everyone. I always look forward to hearing the presentations, and happy to see some new faces that haven't been with us in the past that I've noticed. So look forward to that. So let's move forward.
Great. And so for you, those of you who might be new, I just want to take a moment to let you know what our goals are. And first of all, our primary goal is to give us a chance to learn about other aspects of the energy industry and other aspects of the industry in general, to be able to pivot and utilize your skills and talents in as many ways as possible, because these are different and unusual times, and those of us who are flexible and are willing to open ourselves to new experiences will obviously have more opportunities. So our goal is to open opportunities and also to allow you to meet different people and have different ideas and knowledge about potentially new areas and maybe areas that you hadn't considered in a long time. So I'd like to start by going ahead and introducing our first speaker. Our first speaker is Miriam Winsten, and I'd like to invite Miriam to share her screen and to go forward. So let's see where Miriam is. Great.
Okay, can everyone see me, hear me?
Yes, thank you. Excellent.
Okay, excellent, excellent. Sorry, I had some technical difficulties. I had to leave and come back. But
yeah.
Good evening, good afternoon, and good morning, everyone. I'm speaking from sunny and very hot Central Texas. The presentation today, we're going to cover various topics, such as what is sustainability, what technologies we as geoscientists use, talk a little bit about technology as it relates to sustainability as a whole, and then kind of finish up with geoscience and the impact geoscientists and technology have on sustainability. So we really can't talk about much until we define sustainability. So what is sustainability? When you work for a company or an organization, sustainability basically has three parts. In my last role at Schlumberger, I managed this for the company in terms of producing their corporate sustainability report. And the three areas of sustainability really are governance, how an organization or a company governs itself according to laws and rules and regulations. The second area is social responsibility. It's the social piece, it's health and safety, and how we relate to the communities in which we live and operate. And also includes the relationships that an organization has with all of its stakeholders, including employees, by the way. And the third is environmental performance. That's something all of us can relate to. And all of this is tied together on a global scale as well.
Miriam, I'm going to stop for a second. So can you change your view so that it's the presenter view, because things are looking kind of
sure. Sure.
Great.
Let me see how to do it. Hold on. I think we went through this before, right?
We did.
See.
I think that's, yeah, just.
Is that better? Okay, excellent.
Yes, perfect. Thank you.
Okay, I need better Zoom training. But all this ties together globally under the United Nations. And some of you may have heard of it, some of you may have not, but these are the Sustainable Development Goals. They're put forward for the world, for everyone that lives in it, for everyone that works in it, and they're basically global objectives is kind of a cool way to look at it. And technology and all forms of energy play a key role in achieving all of these goals. While doing that, we also have to meet the energy needs of today, solving energy poverty and providing energy for the future. The big question for all of us is, where does geoscience fit in and how can it help achieve these goals? So just to mention, without going through absolutely all of them, you can see where the shift from fossil fuels and the transition to renewables, climate change, cross-industry transformations, nature-oriented solutions, minimizing emissions and pollution, and there's many, many more. So one of the technologies I'd like to share with you, and some interesting articles I've been reading recently, cover technology and which geoscientists either utilize or can have an impact on, and impact energy and the sustainability in the energy industries. For me, this is a big deal because if you look back, the first example I want to talk about is artificial intelligence. Back in the day, and I know I'm dating myself, but I will, believe it or not, some of you can relate to this, we didn't have computers, or we had big mainframes, but we didn't have desktops. We did everything on paper and had colored pencils. I see Susan smiling because she remembers that. But the thing is, in all my reading, the first definition of artificial intelligence I could find was from 1955. And I thought it was really cool because it basically said it's software that can think like a human, but faster and can churn through reams of data even faster. And we're going to take a look today at some examples of AI and how it's currently deployed in energy. Now, keep in mind, I'm not saying oil and gas, I'm saying energy because it's a much broader topic. Today, the impact of AI is very widespread, and it has been key to complex data analysis and management that we've all used, whether you're in oil and gas or any other industry and you're looking at the subsurface. But it's also used to model climate change, look at air and water security, biodiversity, disaster resilience, and lots of other subject areas. Let's take a look at the oil and gas industry. Just to give you a little bit about my background, I've had over 40 plus years in energy. Believe it or not, I have pivoted in and out of energy and taught at a university in a hazardous materials management program for 8 years. So I'd like to know that I was an early pivoter. And one thing I'd like to talk about, and I'm going to give an example from Schlumberger, I'm going to give other company examples as well, but of AI and big data interpretation, and how it's helped us in our jobs today and how it can impact our jobs of the future. So Delphi, which is an E&P software product, right? It utilizes artificial intelligence and big data analytics. Why is that important, right? We have a tsunami of data that hits us every day, no matter what we're doing. And even the best teams, if we didn't have this, it would take years. And with AI and machine learning and all that good stuff, we're processing data in minutes and lots of it. And why is it important to geoscience? Yes, we can process lots and lots of data very, very fast, but more importantly, very quickly, we can start seeing patterns in the data. for multiple opportunities, no matter what that is. Is it structural? Is it stratigraphic? Is it oil and gas? Are we using it for water injection, geothermal? Is it just so many applications out there? And this is a huge strength for the geoscientists today. The next thing I want to talk about, this is an example from Total, where here's a very practical technology for anyone in energy in the field, for example. Total has deployed these devices as part of their PPE. They're headsets that enable the field operators or anyone working in the field hands-free, so they could be doing very complex work while remotely communicating through audio and visual with subject matter experts, one of which could be a geoscientist, either wearing the headset or on the other end. And this technology has a wide range of industry application for the many new energy technology companies working in the field. For example, geothermal, wind, solar, all have people in the field. Now, this slide isn't about as much as about technology that geoscientists utilize, but looking at it from a sustainability perspective, these are technologies that is shaping sustainability. So this is taking us back again to the United Nations SDGs, as well as climate objectives. So there's 9 technologies. This is from a report by McKinsey. All these slides, by the way, I don't know, Susan, if you're going to share them, but I have links at the bottom on each slide that if you want to read more, you certainly can. And these technologies are shaping our world. Some people say they're in the future, but they're here and they're now, and they're being developed. So the first couple, which are highlighted kind of in purple, all revolve around the shift, current shift, and future shift to electric transport. The first one talks about public electric transport. Currently, McKinsey highlighted there's 160 electric and hybrid vehicle models available today. Compare that to 5 years ago. That's a huge jump. Widespread adoption, for example, in China, there's 300,000 electric buses. Although these e-buses have a higher acquisition price at the moment due to the upfront battery costs, their total cost of ownership is lower because of the independence from diesel, which is very pricey. So as we talk about these, we're not just going to talk about them as technologies shaping global sustainability, but the business case as well. These e-buses, as well as many electric vehicles, eliminate particulates, SOx, NOx, and CO2, all major issues in most cities today. The second is electric trucks. We're starting to see more and more electric trucks being developed. The total cost of ownership here, again, is slightly higher, but should be on par with diesel-run trucks. And it all becomes, along with public transport as well as electric cars and trucks, is infrastructure. That's still being developed today and is just growing globally. So it's predicted that the adoption of these battery electric commercial vehicles could surpass car electric sales in some markets by 2030. Now, for the new age of electric vehicles, expanding the market for lithium and cobalt batteries. And I'm going to mention this probably more than I should, but lithium and cobalt are mined. And who's great with mining? Geoscientists. So just keep that in the back of your mind. The expanded market for the batteries has huge implications Industry, utilities are finding broader use for them, with the price for batteries rapidly dropping. They're providing valuable pathways to reduce power costs and also increase reliability and resiliency. The last issue when it comes to energy storage is long-term. So lithium-ion batteries, now I have a lithium-ion, for example, in my floor sweeper in my house, but they last about 4 to 5 hours. So the market wants solutions that will address long-term storage needs brought on by seasonal shifts. And this is really important because as we move more and more into solar and wind, for example, there are days where we're not going to have a sunny day and we're not going to have a windy day. So we need to be able to have the ability to store that energy for longer periods of time so we can use it on the days when the wind doesn't blow and the sun doesn't shine. And many companies are working on this. Google X recently spun off a company called Malta, which is storing renewable energy in molten salt. You have Ventura Energy trying to solve the same problem by building low-cost thermal batteries for grid-scale energy storage. And if you take a look at even traditional oil and gas companies, BP-backed Lightsource is adding storage to solar development. And there's many other traditional oil and gas operators such as BP, Shell, Total, and Equinor have moved into the renewable space. Companies like Schlumberger have developed a new technologies group also addressing technologies for the renewable sector. So just to move to the bottom of the slide real quick and take a look at accessible solar powered energy. It's becoming cheaper, it's becoming more accessible, a trend that has major implications for the nearly 1 billion people around the world without access to energy. While expanding the grid is part of the access solution, there are many countries like Sub-Saharan Africa and the Caribbean where a majority of the world's unelectrified population is exploring renewable solutions to those areas, whether they're grid-based or solar home systems. I visited a company a few years ago in London called Bbox. It was a startup back then, and for example, they have a contract now with the government of the Congo to basically have solar home systems. It's so important because it plays such a major role in reducing energy poverty in that part of the world. So in this same McKinsey study, they've determined that the solar home systems can help power 150 million homes by the end of this year. So that would be tremendous. The last two I'm going to go through pretty quickly because I know we're short on time, but carbon capture and storage allows industry to capture carbon at its source, compress it, and store it, right? The technology not only has potential to significantly reduce greenhouse gas emissions, business case, it can also generate revenue if the CO2 can be used profitably to make other products. This is so important because our knowledge as geoscientists, our knowledge of the subsurface, and most importantly, our ability to understand and apply complex reservoir models provides us with a key opportunity in this carbon technology arena. The very last thing I'm going to talk about, it's kind of related to carbon capture, is hydrogen. It's really difficult to imagine how we can meet the very ambitious global warming benchmarks without including hydrogen as a critical part of the solution. It's an ideal solution, for example, for heavy cargo vehicles traveling long distances. Hydrogen fuel cells vehicles are already on the road in Japan, South Korea, California, and Germany, just to name a few places. Again, the cost. Here, the cost for producing hydrogen needs to decline significantly. And again, just like we spoke of when we spoke about electric power, infrastructure that needs to step up. But the thing about hydrogen, it can become a very key enabler in this transition. I think one of the most important things to mention here, and I know Denise Cox has mentioned this in some of her presentations as well, that geoscientists and geoscience and the technologies we use and the knowledge we have, whether it be surface or subsurface, play a critical role in the development of both renewable and non-renewable resources today and moving forward. And our ability to utilize software and hardware and artificial intelligence allow us as individuals to interpret and integrate and analyze and develop scenarios to explore and develop multiple types of energy for our world. And here's just a few examples of how our skill sets fit into this puzzle. And I would just like to end with a few important notes here. For all types of energy and industry goals and the UN Sustainable Development Goals, and for example, IECA, who along with their member companies produce the guidance for the oil and gas industry for environmental performance and social responsibility, is aligned with the SDGs. All industries are aligned here to produce results towards these goals. And I can't not mention, and I can't not put a plug in for AAPG because it has been so important to me in my life, providing networking and education and so much more, and for all of us to continue learning and pivot to wherever our skills take us. Thank you.
Well, thank you. And thank you for mentioning AAPG. And these are times where we're really changing quickly, and AAPG is really committed to trying to do all we can to help people. So this is great. And thank you so much for a fantastic presentation. So just to let everybody know in the audience, we had a few technical difficulties at the beginning. So we're going to be running a little bit late, but just relax and just enjoy. So I'm happy to introduce our second speaker, Edith Newton Wilson of Rock Whisperer. So welcome.
Thank you, Susan. Can you hear me?
Yes, perfectly.
Great. I wasn't able to turn my video on, but if you'd like to, feel free to. Otherwise, I'll just speak to the slides.
Okay.
I'm Edith. Is that something you'd like to do?
Okay, you should be able to turn on your camera. Let's see. I see your slides. There you go.
There we go.
Yay.
Great. I don't know why, but I feel better with a virtual presence because we are all so far from each other. And before I begin, I would love to shout out to some old friends who are on the phone, Terry Olson, Kevin Toast, and Flover. Hello, all of you. It's good to see you virtually, and everyone else, of course. I'm beginning with this slide, which is, I think, really a great description of my personality and what has driven me in the energy business for 30 years. And that is that like I suspect most of you on the phone, am an explorer first and foremost. I like new things. I like going into areas that I don't know anything about and finding out how I can do something productive for society to provide energy. I feel like the mission of all of us, and it has been since I first started working for Amoco 30 years ago, is exactly described in SDG 7, which is to ensure access to affordable, reliable, sustainable, and modern energy for all, energy equity across the globe. So I feel the most exciting thing we do as geoscientists is we don't follow the path. We make the path to parts unknown and leave a trail for others to follow. So the rest of my talk is going to be a snapshot of where we are today with respect to the market and the economics of the energy transition. And I'd like to describe it as an economic imperative that is really driving the transition. We're all aware of the impact of climate change on our planet and on human habitability on the planet, and we all want to do the right things to make energy more sustainable. But at this point in time, it's really commercial opportunities and economics that are driving and accelerating the energy transition as we speak. And I think that provides a lot of opportunity for us as earth scientists to pursue. So as promised, this first slide is simply a snapshot from the most recent April report of the International Energy Association, which I find to be the most objective and global assessment of energy data worldwide. And they're looking at the impact of the pandemic on energy. And what you see in these three slides are three very clear indicators of a slowing in growth of demand for energy. And along with that, as part of this, as a result of this great pandemic experiment that we're all living through, we see a cliff, a falling off the cliff in terms of CO2 being emitted into the atmosphere. So greater and more substantial than during the Great Depression or the pandemic which preceded it, which you can see there around 1920 in the upper right, greater than during World War II, the oil shock. We are seeing what control we actually have over carbon emissions in the way that we use energy. These are data. This is a picture of an experiment that we did not plan, but we have the results now that we can use. What that's meant for the markets is we are seeing in 2020, according to the data, a drop in demand for almost all fuel sources with a small rise in demand on the upper left for renewables, but total energy demand really going through the floor. And if you want to look at that by country or region, there's some really significant diagrams, I think, in the IEA report that just confirm that really the least drop in demand growth is, as expected, going to be in Southeast Asia, Africa, and India, while the so-called developed world is experiencing a much greater drop in demand growth. So Woodmack puts it very well, I think. There's a beautiful paper out there that I think makes really good reading. Could clean energy be the winner of the oil price war? Now, is it really an oil price war or is it a demand drop from the pandemic? Regardless, we are seeing a shifting of our landscape and we are seeing an acceleration of the energy transition. The slide on the right is a nice depiction of our current energy companies, mostly oil and gas driven, based on segregated according to their push for carbon neutrality on the y-axis and their new energy or clean energy diversification on the x-axis. So I think that we see a group of what I call the survivors emerging here on the upper right, those companies that are pushing for a low carbon future, that are diversifying their energy portfolio. And my guess is that this big cloud on the lower left will probably consolidate into a couple of what I call super producers, companies that are really focused on providing the oil and gas that is needed to supply the baseload as the energy transition comes in. But the curve on the far right shows that even at times of rising oil prices and rising oil production, the acceleration of the renewable energy curve continues unabated. And so I think we're all going to need to start looking at the names in the green circle, NextEra, Enel, EON, and there's Warren Buffett right in the middle of it all. These are the companies that are building the big wind, solar storage utilities that are going to replace fossil fuel generation. And as Miriam pointed out so beautifully in her slide from McKinsey, the real driver behind this, I won't bore you with a bunch of economic slides, but we all know that wind and solar are now cheaper than natural gas for producing power. But the real driver to enable this energy transition is the lithium-ion battery. And this is a curve that is familiar to anyone who's looked at technology development curves, say from Silicon Valley in the 80s. This crossing of price dropping dramatically and production and productivity going up concurrently is very descriptive of the change in the energy business that we are all living through. We are no longer working on an extractive, mechanical, long life cycle, capital intensive, high risk business. We are working in a technology world now where things happen dramatically fast. As a matter of fact, this slide, which comes from November 2019, so less than a year ago, could barely envision just under a gigawatt of energy storage by 2025. Now the market analysis that looks at what's actually funded, under construction, is looking at 2 terawatt hours by 2028. So every year we relook at these predictions, and every year they were wrong on the low side. What does that mean? That means we need material. We need material for the batteries. We need lithium. We need graphite in great quantities for the anodes. We need cobalt. We need places to process the lithium and get it to battery grade for the batteries. So all of this means geology and mining, of course, but what I really want to emphasize for everyone on the call is that for the supply chain for a battery, mining is only a very small part of it, and it's an important part, and all of the tools that we use in mining for exploration, well data, et cetera, are very familiar to us all, resource assessment tools. But that's just the start. I love this series of photographs on the bottom from my friend Jesse Edmondson, because it shows that there really is no value in the excavated product. There's a little bit of value added when we go to a concentrate, but then an order of magnitude of value gets added in the turning of that ore that is mined into an advanced material that is really bespoke for the customer who has acquired it. Now, the slide I've chosen here is from Volkswagen, where they show mining to refining to cathode production, cell assembly, et cetera. What I find fascinating is just today, after I had put this slide together, BMW announced that they are buying into cobalt and lithium mines in Morocco and in the Lithium Triangle. So the OEMs, the manufacturers of automobiles and batteries, and we all know Tesla's building gigafactories, as China is as well, the OEMs are actually going into the mining business to secure supply. Now, this sort of change from an extractive industry being the focus to the value being added closer to the near surface is also true in the geothermal world. You know, we're all familiar with the fact that sort of old school geothermal was drilling deep, hot wells in places with volcanoes. But what's happening now, especially in Europe, but also, I don't know how many of you tuned in for Pivot 2020 last week, but we are seeing a push to exploit all of the heat in the earth, everything from hot, dry rocks in the crystalline basement to what's sitting in my front yard here in Tulsa, which is a geothermal ground source heat pump at the very shallow end. We can make use of all of this heat, and we need all of our geological know-how from earth surface to aquifer development, all the way down to fracking the crystalline basement in the deep geothermal wells. Now, I'm going to close, and I hope I maybe get us a little bit back on target here. I'm going to close with a couple of things that I think are really important. If you're bit by this bug of new exploration like I am, and you're interested in being part of, sort of being on the front end of the energy transition, there are two things that I'd tell you to do. The first is talk to some people who are actually doing it. And so I've got a few people that I want to introduce you to virtually. You can find them on LinkedIn, and they'll be happy to answer all of your questions. Lucy Crane and Jesse Edmondson are in the mining business. Lucy works drilling geothermal wells and stripping lithium from them in Cornwall. And she's also head of Women in Mining in the UK. Jesse is an Arkansas grad and was a tree ring, had a master's thesis on tree rings, and now he is the owner of two businesses looking at, and I love the way Jesse talks about this, he's looking to develop a sustainable supply chain for battery minerals. Not a mining business, but the developing this supply chain all along the way. He has a deep appreciation for how important the processing to advanced materials is, and the skills that are going to be needed there in engineering and material science, as Miriam mentioned earlier on, very, very important. A couple of other people that I find fascinating, also very accessible and approachable if you'd like to talk with them about their careers. Taylor Maddie is a friend of mine here in Tulsa who works for Baker Hughes. He's their global geothermal group lead. And he has some very exciting projects and looking particularly at this interaction of old oil field infrastructure with new geothermal opportunities. And Kevin Toth, who I think is still on the call, has petroleum geoscience degrees from Texas and OSU. And about a year ago, he took off for Manhattan, where he now works building livable cities with a big global conglomerate called Arcadis. And I think that if you are aware of AGI's prediction that most geoscientists will be working in risk assessment and finance, and you've scratched your head and sort of wondered what that means, talk to Kevin, because the built environment and how we assess risk and how we build livable, resilient cities and how clean energy comes into that and is integrated into it with AI is definitely the wave of the future, and it's very exciting. And I know several other friends that are going into project management. The other thing I recommend you do is read things outside of your comfort zone. Read green tech media, read Utility Dive, go out to Bloomberg New Energy Finance, Forbes, and don't be afraid of these headlines. They are scary, but if you read through them, you will find so many wonderful opportunities. Big, huge wind solar storage projects going in all over the place, energy efficiency jobs out there, distributed energy resources going in to ease the unelectrified parts of the world. My favorite quote that I'll leave you with comes from a founder of an energy management startup working on energy efficiency here in Tulsa, Dan Frey, who says, "The world is overrun by cheap and plentiful clean energy. How do we adapt?" And then I'm a science fiction fan, so I threw in my little Dune cartoon here with Moab Dib. Remember, if someone is trying to make you afraid of the energy transition, fear is the mind killer. There's a lot of fun stuff to do out there, and there are a lot of great opportunities. Just talk to people who are doing it and read about it. Thanks. I'm done, Susan.
Oh, thank you, Edith. That was fantastic. And a few people asked in the chat whether or not we will be sharing the video. And yes, absolutely. Look for an email from me within a few days, and it will have a link to the recording. So thank you. And our next speaker is Cynthia.Dacre of Maxar, and we'll have a big picture look. So I'd like to invite you to share your screen, and we'll get perfect.
Thank you, Susan.
Looks great.
And, thanks for the earlier speakers, because they provide a nice segue for some of the things I'll be talking about here. Today I'll be talking about using satellite data for carbon stock mapping. And given that this is a lightning talk about a complex subject, it will be a bit of an overview. But since it's a dedicated thing, what I hope you take away is, first, from a perspective, It's important to have these and it's important to have the flexibility to use multi-source, multi-scale, and multi-temporal data when you're doing these type of analyses. But then number two, given that this series is dedicated to pivoting, I want to express that there's abundant opportunities for developing new approaches here. And any of these could help to enhance or even transform the way that these types of assessments are done. Well, as I go through, I'll be calling out some of these as quote-unquote research opportunities, but you can actually think of them as opportunities for improvement or enhancement. And this is something that we find all the time, that we're continuously tweaking our science here, and we have a need for people who can look at things from different perspectives to help us with this. So first, by way of introduction, I work for a company called Maxar Technologies. It was formed when longtime space leaders MDA and Digital Globe joined together a couple years ago. One side of our company builds and operates satellites, and the other interprets satellite imagery. Right now, we operate 4 very high-resolution optical satellites and plan to add 6 more beginning in early 2021. But we use other satellite sensors as well when completing projects such as the ones I'm going to describe here. So, true confessions, I am actually not an expert in using satellite monitoring for greenhouse gas-related issues, but I work with people who are, and today I'm going to be sharing some of the information that I've picked up from them in recent years. The reason I got involved with this topic was because we were getting so many requests for help. As you know, the carbon market is fairly large and growing all the time. In addition, energy companies are under pressure from financial institutions and other stakeholders to be carbon neutral, and various forms of carbon sequestration are part of that equation, as Miriam alluded to. Various satellites are used to track emissions and place them in context, and also to monitor changes in biomass that can affect an area's carbon stock value. This chart provides an overview of how satellites help with this. Don't be thrown off by all the words. Pay attention to the orange boxes, okay? There's 2 general approaches. Top-down, which use satellite-derived information to track atmospheric greenhouse gases, and bottom-up, which is used to evaluate the initial carbon stock value of an area. And then we use that to monitor how that carbon stock value is changing. I'm going to talk a little bit about evaluating atmospheric carbon and a little bit about above-ground biomass, but I need to point out that there's a huge need to better understand how to remotely characterize soil carbon. So we won't be addressing that today, but that's the first research opportunity that I want to call attention to. And you can see the numbers on the lower right-hand side as far as the pool and petagrams for each of these 3 components. On the left side of this slide, we see an example of top-down monitoring. It's a map of methane concentration that were derived from a satellite named Claire from a company called GHGSat. In order to place these results in context, they're displayed against a backdrop of high-resolution optical satellite imagery. Claire is actually a demonstration satellite, and its data has a spatial resolution of about 50 meters. GHG's next satellite, named IRIS, will have a spatial resolution of less than 25 meters, and we're hoping that that will be launched within the next few weeks. Now, in the upper left, you see a chart of various other planned GHG satellite missions. Most of the ones that are listed as science provide data at spatial resolutions of several kilometers. But you can also see that there's many upcoming launches that will provide data at resolutions less than 1 kilometer. So we're expecting that the top-down approach to really take off as a lot of this detailed data becomes available for the first time. And so this is another opportunity to perform research or to enhance the science as we know it. Now, on the right-hand side is an example of what we look for in a bottoms-up approach. Here is a burned tropical forest, and that burning will have a negative effect on the area's carbon stock. So ideally, in evaluating an area, we would use both optical and GHD data, and with the new satellites being launched, we will have the opportunity to do so. This slide shows the benefit of using multi-scale and multi-temporal GHD data, in this case for top-down monitoring. On the left side, we see medium resolution imagery from the tropomi sensor on the satellite, on the Sentinel-5 satellite. The far left shows results from March and April of 2019. But the figure immediately right of that shows how things changed during the same months in 2020. The increase is probably due to increased flaring that occurred when the oil and gas prices dropped so low. So in this case, it's helpful that we were able to look at this wide footprint that the medium resolution imagery provides, and also to be able to consider data acquired over several weeks so that we can identify and track these regional trends. But on the right side, we see high resolution results, once again from GHGSat's CLARE satellite. It's taken over a small portion of the other viewing field. On the medium resolution imagery, if you look at the box that's enlarged to the right, it doesn't appear extraordinary in any way. But the higher resolution image shows that there is indeed a hotspot here. So this demonstrates how using higher resolution has the advantage of highlighting areas where some sort of action may be needed. The same concept of using medium and high resolution analysis applies to the bottom-up method too. This table shows the UN IPCC's tiers increasing in reduced uncertainty as one moves up along the left axis, and the various approaches that provide improved representation increasing toward the right. Over time, the way that these analyses have been done has gone from the lower left-hand, trending in the lower left-hand corner up toward the upper right-hand corner. In other words, it's gone from very simplistic approaches of tallying up values based on the percentage of general land cover class categories toward a multi-temporal geospatial analysis that considers how the land use is changing over time, because that is how actionable items are most readily identified. And this slide shows some of the ways, some of the reasons why this is done. With higher resolution satellite imagery and also geospatial analysis, we can pick out the fine details such as where fields are being tilled, where revegetation is occurring, and even identify trees down to the species level. This level of detail may or may not be of interest when completing a continent-wide assessment, but it's usually needed or at least considered when evaluating the area around a client's assets or specific holdings. Now I'd like to just touch on the way that carbon stock analysis is actually done. In all cases, biomass or carbon values are derived from fieldwork and used as an input. These values may be either from site-specific work or from analog sites found in literature. They're correlated with some aspect of the remote sensing data using one of several potential approaches. And the specific approach is selected based on factors such as setting, data availability, timing, or budget. And then field-based correlations between biomass and carbon stock are used to derive the final values. So in the interest of time, we're going to take a look at these approaches, but go through them pretty quickly. The optical method only uses direct regression models with above-ground biomass from field plots correlated with variability in the field forest stands that are described by satellite-derived parameters such as texture, as shown in the upper right, or vegetation indices, band ratios, or other spectral properties as represented in the lower right. The approach known as stratify and multiply is essentially completed by creating a land cover map and then using a single value for each land cover type. It can be a very general category such as deciduous forest down to the tree species level of detail that we showed earlier. The forest structure may or may not be considered in this approach, and if so, that can be derived from radar, LiDAR, or extracted from optical imagery. Both the optical only and the stratify and multiply approaches are widely used, but these are continuously being enhanced through ongoing improvements in remote sensing techniques. So once again, using these present an opportunity for scientists to improve the existing technology as we get more information and the science matures. SAR stands for synthetic aperture radar, and with this approach, forest structure is correlated with biomass through direct regression or machine learning. But here's another upcoming opportunity for additional research. The longer the wavelength, the more SAR can penetrate into the tree canopy and provide accurate information about biomass. The chart on the left shows that the chart on the right shows that most current SAR satellites operate at the higher X-band or C-band frequencies. But there's two noteworthy upcoming launches of satellite that will provide SAR data at the L-bands and P-band wavelengths that are expected to be ideal for mapping biomass. Once we have the availability of these data, it should provide lots of opportunities for enhancing our analytical methodology, hence another opportunity for those of you who are looking to pivot in some way in this field. And last but not least, there are recently launched satellites that use LiDAR to provide some measure of forest structure. Those data have some gaps and they're not necessarily at detailed resolution, but they will definitely be useful and are already providing insights into biomass mapping. So in summary, satellite imagery is used both for top-down and bottom-up carbon analysis. And there's value in using multi-sensor, multi-scale, multi-temporal data to get a thorough picture. High-resolution images are used to identify the actionable items, but most importantly for this group, I think it's important to consider that we expect to have quite a few technical advances over the next few years because we're going to have suddenly a lot more available satellite data that's a little different than we had before. And so this provides a lot of opportunities for those of you who are looking to pivot into this field. That's all I had, Susan.
Well, thank you, Cynthia. That was fantastic, and I really appreciate the fact that you're pointing out opportunities and the new technology. So that's great, and we'll be sharing email and contact information for the participants as well as a link to the video. So if anyone would like to get in touch, that would be great. So I'm really happy to be able to introduce our next speaker, and Ana D'Alessio. You might think, well, this is an interesting transition to go from satellites to 3D printing, but we're trying to think of tools and basically the way that processes are changing in our new world. So welcome, Anna.
Hi, thank you. Sorry about that, just trying to unmute myself. So thank you. My name is Anna D'Alessio. I am the Director of Quality Engineering at Ivaldi Group. And so we are looking at providing additive manufacturing solutions for the heavy industry. So today I wanted to talk about 3D printing for sustainability with a focus on spare parts on demand. Sorry, okay, so the problem that we've really identified is that no one wants to carry inventory. So if you think about a physical warehouse and all the parts that are in there and how expensive it really is to house these parts and then get them to the end user. So there's a high cost of delivery and getting them there is very expensive. And so there's a lot of missed opportunities here. And so what we're trying to do is really solve this problem, and we do so focused on 3D printing. So the solution is actually send files, not parts. So we've seen this in the past, but what we're focused on is turning a hardware problem into a software and services opportunity. So as opposed to having a physical warehouse, we're focused on storing all of these digital files for those parts into a digital warehouse or digital inventory that can then be sent to different manufacturing sites around the world, printed close to the end user. So we've seen this before in the past with things like Blockbuster, and now everyone can stream whatever content they want on demand using Netflix and things like that. So we're kind of using that same sort of approach just for the spare parts industries. And so we're doing this by taking the traditional process and actually combining a lot of those steps into what we're calling the part replacement as a service. And so traditionally, in order to get a final spare part to the end user, there's a lot of steps that go through in just handing off from person to person when placing orders, approving orders, contacting multiple suppliers to see who has the part on hand, how long it will take to get, and what that cost is, as well as that physical delivery to where you are. And so what we're proposing to do is actually, once that part is consumed, you can place the order automatically, which searches a global database, and then those files can be sent to wherever you are, as opposed to you coming to that part and then delivered to that end user. And so the benefits of 3D printing are that the cost of each individual part is relatively the same, no matter how many parts you're making at once. So with conventional manufacturing, there's usually this really high setup cost or initial cost, and you don't really get to a cost-effective part until you're producing high volumes of parts. Also with 3D printing, you can create very complex parts that you wouldn't be able to make otherwise, and make different features or internal structures that you could not make using other technologies. And so kind of tying this back to sustainability, I wanted to talk about these benefits as they relate to the 3 pillars of sustainability. So thinking about the planet and thinking about all the waste in the world. So 3D printing helps us to actually reduce material waste, because as opposed to starting with a block of material and chipping away at it, you're actually starting with basically nothing, just a flat base and building up. So you're building up that shape that you actually want, as opposed to cutting away at it. And using 3D printing, you can actually create new designs that you wouldn't be able to make through casting or injection molding or even machining, which means that you have this opportunity for increased part performance within a system by creating these new parts or spare parts that you couldn't otherwise make. It also is helping to increase equipment lifetime, as opposed to buying whole new equipment. You can source spare parts, you can source just the broken components and things like that, and continue to use that equipment longer and longer. And also, you only have to supply the needed spare parts, which means that you're not making parts that are going to go unused. You're not forced to ship parts around the world that are going to go unused, thinking about the effect on the environment in terms of transportation, that shipping or transportation cost. Looking at people, so this is actually helping to create local jobs, because we're talking about distributed and on-demand manufacturing. So bring manufacturing to the end user. So if you need a part in California, as opposed to having something shipped all the way from Europe, you could actually manufacture it in California and bring it right to your end user. So it's also helping to de-risk the supply chain. So we've seen, especially in this time of COVID, the fragility of the supply chain around the world. So instead, you can actually reduce all of those steps and take those risks away, so you can get those parts faster. So it's improving lead time as well, just because that transportation that is not necessarily there, and improving that procurement process, as opposed to contacting multiple suppliers and waiting for quotes to come back and approved and all of that back and forth. It's kind of a direct ordering system straight to the part that you want, which is then made where you need it. And then looking at profit or economic, there's an increased profit margin, because you're only paying for what you want when you want it. We also have the ability to create smarter parts. So this means embedding sensors in these parts as they're manufactured, which is something you couldn't do with traditional manufacturing. And these sensors help to predict maintenance as well as wear, so that you are actually reducing the unexpected downtime, which of course is a huge savings across the board in all industries. It also means for no minimum order quantities. So usually you think of a small part that may be very critical for you in that time, but you may need to buy 100 of them just to get them to you at that time, and you only need 1 or 2. So 3D printing allows you to actually just make the part that you need and order the part that you need. Again, it's reducing overall lifetime cost by increasing your equipment lifetime, which is saving cost as well. And of course, reducing that physical inventory cost. And so I wanted to just show a couple of examples of 3D printed parts and components, just to give you a sense of what I'm talking about. So the first image on the left that I want to talk about is actually a crank pin. And so what happened was a piece of this crank pin broke, and as opposed to buying a whole new one, we are able to 3D print and just repair the part that was broken and put this back into operation. And then if you look actually in the middle on the top, this is a pump that was, is an example of polymer 3D printing. So this was something that we were able to redesign in order to decrease the amount of parts, make it so that we could source just the spare parts when components broke, if they did, and we were able to increase the efficiency of the pump. Then looking at the bottom, this is a cross-sectional view of an impeller. And as you can see, there are these internal cavities. So the traditional manufacturing process for this was casting. And with casting, you would not be able to make those internal cavities. So we redesigned the part. We were able to save weight. So the weight of this part was actually a savings of almost 30%. And we're in the process able to do some redesigns for that manufacturing technology of 3D printing and increase the performance here. And the last part that I actually do want to point out is the one on the right, which is a thruster. As you can see, there is a lot of different components here. And if you think about just one of those breaking and then having to replace the entire system, how much time that takes, how much of a hassle it is, how expensive that would be. So in this case, we had a broken blade. We were able to 3D print just the blade, install that within the thruster, and then put that back into work. And so there are a lot of benefits to 3D printing that do affect those three pillars, not just the economic side that people tend to think of. And so the last thing I really want to talk about is putting this all together in terms of the product life cycle. So thinking about all parts in all industries, we're starting with a raw material. We've heard this before. It's transformed, it's produced into the parts, assembled, sent to the end user in use, and then it reaches its end of life. And then what happens? And so 3D printing actually allows us to do something with that as opposed to just having those parts go to waste. So repair and remanufacture are the two big ones. So repairing a crack or a break or something within the part, you can do that through 3D printing, traditionally through processes pretty similar to welding, but to get that part back into use and continue to cycle that through. Remanufacturing is also just building up wear before something breaks, so to avoid the actual downtime that you would normally see as parts break in systems. So predicting that, remanufacturing it, and continuing it through the system. The next thing I wanted to talk about is actually hybrid manufacturing. And so this is a combination of subtractive and additive manufacturing. And so if we look at subtractive manufacturing or something like machining, like I think everyone is familiar with, you start with a block and you chip away at it until you get to the shape that you're looking for. And then you're left with a lot of scrap or waste, which can sometimes be recycled and sometimes not. With hybrid machining, you're actually just starting with a base plate. You're building up and you're building that near net shape through 3D printing while leaving those internal cavities and other features as you build them. And then you just use the subtractive manufacturing or machining in order to achieve the tolerances that you want. And so you're actually left with an accurate part that has features that you wouldn't normally be able to make. And that also means that there's less waste or less scrap at the end of the process. And so one of the things that Ivaldi is doing actually is taking all this into account and looking at recycling materials for the spare parts that we provide. So recycling those materials once they reach their end of life for whatever reason, turning them back into the raw material or filament that we're using to 3D print, and then distributing them again to the end user to be put back into use and continuing the cycle. So really what I want you to take away from this is that what we're trying to do with 3D printing, if we can close the gap, we can reduce the impact that manufacturing tends to have on the environment, on society, and on economics. And it really is very specific to the industry that you work in as well as the company that you're in. So there's a big difference in the types of parts and the savings that you're going to find. And you have to build a business case for your specific company in order to figure out what that is. So I just want to say thank you for your time. That's all I have, and I will pass it back over to you, Susan.
Well, thank you, Anna. That was amazing. You went through so much and it was so clear and really quick and very quickly. So we have some questions from the audience. So I'm looking at chat here. So first of all, Anna, there was a question for you. So does Ivaldi sell 3D printers for aluminum?
Not exactly. So we're focused on more on screening part data and procurement data, as well as digitization for 3D printing. So to bring your inventory into, put it into a way where you are ready to 3D print it. So we're not actually selling 3D printers, we're using 3D printers, and we have partners that make various 3D printers around the world. So the short answer is no, but there are lots of 3D printers that do 3D print aluminum parts.
So it's basically print on demand?
Yes, exactly.
So well, my question is too, like, okay, so in additives manufacturing, if you have, say, aluminum or some other metal, and it really has to be, have the strength of materials, how do you test the lattices to make sure that they're really holding?
Yeah, no, that's a great question because that's a big concern across all the industries that we're working in. So we've been involved in a lot of programs actually developing quality standards and certification standards for these spare parts that are produced through additive manufacturing. So really what it is it's first qualifying the machine to be used, then qualifying the material for the machine. So 3D printed materials are a little bit different than what you may normally think about because a lot of them use these really fine powders that have been manufactured specifically for 3D printing and specifically for the machines that they're in use for. And so that goes through a series of tests, mechanical testing, chemical testing, et cetera, in order to ensure that the part that you're getting is what you expect. And then once you're actually 3D printing the part, it sort of depends on criticality of the part. So as you get into something that's more and more critical, you're going to be doing more and more testing, and you're probably going to be printing a second part that you actually put into a designed fixture and test in itself to make sure that what you are going to put into service works the way it does. But a lot of it is done through test specimens and test coupons, sometimes prolongation of parts that can be tested. But there's a lot of monitoring within the process. And a lot of also, we do a lot of digital simulation before printing so that we have a sense of what's going to happen to the materials as you print them. And as you get into metal 3D printing, there's a lot more that you need to do in terms of the thermal history of the part as it's printing.
It's just so interesting because, I mean, I keep thinking of mineralogy and optical mineralogy and crystallography, and there's so much there's so many parallels. So it'd be interesting for geologists to take a look at that, especially the strength of materials, and as the process, just how it's tested. That's fascinating. Well, thank you. Yep. So Edith has a question. Okay, good.
There. Yes. I have a question for Cynthia. And Cynthia, I was fascinated with all the work you're doing, especially on greenhouse gas emissions from land use, because I used a carbon calculator for the first time last fall and found out how much my diet is impacted by, or how much my diet impacts my carbon footprint on the basis of land use. So I thought that was fascinating. But my question for you is a little bit different and overlaps with some of the comments that Miriam made and that I discussed. And that is that as we move into a world of distributed energy resources, I've been wondering if some of the technologies you are using for monitoring carbon can be used to try to assess the growth of distributed energy resources, particularly solar photovoltaics in unelectrified parts of the world, sub-Saharan Africa, China, India, parts of Brazil. I have solar panels on my home, and my electric utility doesn't know when I generate solar and use it. They only know if I sell it back to them. So there's this little wedge of the market that we're underestimating because we're not able to get a handle on how much energy is actually being generated. Do you all do any measurement of solar photovoltaics?
So we have actually different parts of our company that that I know do touch on this topic, and I'm not sure whether, because we have a lot of different projects and I'm not familiar with all of them, whether, how it's pulled together for how I understand your question. But let me just mention a few ways to address this. I know that one issue that we had in dealing with Africa was just identifying where there was where there's settlements, and we use night lights, for example, to find that. We see, especially since, with the, people have cell phones and computers, et cetera, that they're using for light. We can use nightlight technology and look for where there's some sort of settlements. We use artificial intelligence, a combination of artificial intelligence and crowdsourcing to identify solar panels. You wouldn't think it would be that hard, but sometimes you just need a set of human eyes on it, and crowdsourcing is a technique that allows us to do it very quickly and very efficiently. We run the AI analysis to do a preliminary find, and then the crowd helps to perfect it. So we have done regional mapping in remote areas looking for solar panels. But awesome. I'm not sure what the size limit is, et cetera, that's been used in those actual applications. But anyway, and then of course we also have we have a meteorology group that deals with solar and wind, and so there's only certain parts of the world that might be suitable for some of these things. So we're able to kind of focus in where to take a look from that perspective too. So
right.
Excellent.
It's just such an interesting aspect for opportunities for geoscientists as well, because that application of GIS with remote sensing, and I hadn't even thought of the crowdsourcing aspect of it, but all of that, those are skills we use for another purpose, but for energy measurement, I think there's a real opportunity there. And
as far as from a technical perspective, it's all exploration. Yep. It's all trying to find that thing that nobody's seen it in the way that you're going to see it,
Exactly, yeah.
Excellent. Okay, so we have another question that came in. Oh,
there's another question up there for Edith from Robert Gales.
Oh yeah, I was going to ask. Okay, great. Okay, good. Go ahead. I was going to do this. Great. We'll go to Anna after that one. Robert, do you want to ask the question, or do you want us to read it? Okay, so good talk, Edith. Why less emphasis on geothermal compared to solar and wind as renewable for baseload and heating to reduce electric and storage demand? Less overall environmental impact than mining and long-term disposal of waste.
Okay, good question. And I will tell you that the main reason for that in my slides today was a history of the last 2 or 3 years in studying costs. And geothermal costs have remained substantially above what I call the triumvirate, which is wind, solar, and natural gas. So the cost of geothermal, although it is great baseload and it's 24/7, but it is big capital investment, it is long-term, and the costs have not dropped as dramatically as wind, solar, and natural gas, so particularly solar. So, and with the drop in cost of lithium-ion batteries as well, then that sort of takes care of the lack of baseload. So, so really that's an economic argument. But what's happening, and just literally in the last few months, is that the focus on geothermal has gotten so much attention in recent days, I think in part because we're faced with all of this well infrastructure in sedimentary basins of the world that we're looking for something to do with it. And we're seeing that we have this resource of heat that every time we drill a well, we have access to and we're not using. So we're seeing a phenomenal resurgence of interest in geothermal, particularly sort of warm geothermal and cool geothermal. But we're seeing the geothermal industry as a whole just explode with new businesses. And so I would expect to see those costs to come down and meet, you know, what the current winners are today. But that's the reason. It's really the commercial drivers.
Great, thank you. So Larry, did you want to read the next question?
I have a question for Anna. Can these 3D printers reproduce or make fabric items, or do they have to be metal or plastic?
So that's a great question. So there's, right now it's mainly polymers and metals. I know that there's a lot of work trying to be done to make textiles and things like that using 3D printing. But if this is going towards the idea of PPE, it'd be very difficult to 3D print something like a lab coat or gloves or something like that.
Okay. Stephanie Jordan also has a question for you. Stephanie, you want to read your question?
She kind of just touched on it. I was asking about the cost effectiveness or the sensibility of hospitals and dental offices being able to print their own gloves, PPE, and even hospital beds. So instead of countries and states fighting over supplies, being able to locally make that, if that makes sense, or if that's a stupid idea. That was all kind of the same thing.
Yeah, so actually we've seen the 3D printing community actually come together in the time of COVID and create different parts of PPE and different things that you could 3D print. So people have been printing face shields, they've been printing, even there's some approved masks that have been 3D printed, and ventilators and things like that. That would definitely be something that hospitals could use. Would definitely help in this sort of situation. And I know that there are also some 3D printing companies right now that are looking into actually 3D printing the filters for face masks. So reusable filters that you'd be able to use in a hospital. So as opposed to worrying whether or not you're going to have to reuse a disposable N95 or whatever, you would take out the filter from your mask and have that sanitized, and that could be reused. So there definitely is potential there. But I'd say it's a little less so for things like gloves, and again, like lab coats and things like that. That would be much harder to 3D print something that would work the way that it is. But there are some dental offices also that have 3D printers. After scanning your teeth, for example, they can 3D print a mold of your teeth, show you that, show you kind of the problem points. And that also is used a lot in the aligner, aligner industry for your teeth as well.
Well, it seems like dental offices could use the printers to make the hardware for dental implants.
Yeah, I think that there's a lot of potential for that as well. Yeah, especially if you can scan it. So a lot of dental offices and orthodontists have the scanning equipment, which makes it pretty easy to then create a model that you can 3D print. It's just in terms of getting the right materials that are approved in order to be implanted. Mm-hmm.
That's great. So looks like Robert has some more questions. Let's see. Anna, on metals, are there temperature and strength limitations?
There are, but just like there would be in any sort of manufacturing technology, there are just limitations based on the materials that exist. I will say for the most part, if you look at something like stainless steel, the properties of a 3D printed stainless steel part is very similar to the properties of a traditionally manufactured stainless steel part. It just sort of depends. So with 3D printing, you have the ability to actually play around with the internal structure and play around with things like density if that is not something that is needed for your final part. So there's a lot of opportunities to save weight if strength is not as much of a concern. But most 3D printing technology is somewhere between 97 and 99% density, and there are post-processing techniques that can be used in order to bring that up closer to 100.
Great. So I have a question for Miriam. Miriam, when you on the array of different sort of drivers of change, which one do you think has been the most affected by the pandemic?
Well, I think I know Edith touched on this. I think the dramatic drop in the use of energy. You know, people aren't going anywhere and they're not traveling. And we've seen a dramatic change in, you know, emissions. And, you know, a pandemic is a bad thing. You can't sugarcoat a pandemic. But, you know, one of the, I think, unintended consequences has been the drop in emissions. I know for us, personally, that's definitely been true. Just looking at how many times you filled your car up with gasoline since we've all been quarantined, right? I mean, it's to the point where it's that basic. I think in a way, and it's fueling the transition, right? As Edith mentioned, we're looking at all kinds of new technologies falling into place now. And it also has impacted the oil and gas industry dramatically, as we've seen, those of us that, you know, either are in it or looking at it or pivoting in and out. It's had an incredible dramatic effect. And to Hannah's point about 3D printing, you know, even in oil and gas, they've been 3D printing parts for a while. I just want to mention that because I really enjoyed your presentation, Anna. And I think with the disruption in supply chain, and we didn't really talk that much about supply chain in the pandemic, but from my own personal experience again, and I'm sure we've all had the same thing, what have you been seeing in the grocery stores? A lot of empty shelves, right? I went to Target just the other day and I was excited because I saw more stuff, you know, and these people need. So there's a lot of impact there.
That's a really good point. In fact, I was thinking specifically of bicycles and things like that. Combination of increased demand and supply chain collapse. I'm surprised that there aren't more bicycle parts, or there probably are, being 3D printed.
Mm-hmm.
So we have time for one more question. Would anybody like to jump in there and open your mic and ask a question? Well, I just really appreciate the presentations today. Larry, do you have any final words?
Oh, just very good presentations. I'm especially fascinated by this 3D, the 3D presentations we've had over the weeks, and I'd like to even know more about that. It's kind of beyond my mind of how it works.
Well, I think it's great. And I think one of the things I appreciate too is just the focus on opportunities. So as we kind of wrap up, we start thinking about looking forward to viewing the recording, I think that if we look at each section, we'll see that if you do an assessment of your own skills and interests, you'll find definitely some kind of opportunity. And to me, that's really the exciting thing about this, and really want to stay open to suggestions and ideas. Next week, we're going to have, let's see, what are we next week? Well, I don't remember, but we have space coming up, and we have drones coming up. We have battery technology and minerals and critical minerals, just everything you can think of we're trying to cover. So anyway, so thank you again. to thank you, Miriam and Edith, Cynthia, Anna, and thank you, Larry. And also want to thank our marketing director, Julie LeMaster, to thank her for all that she's doing. And we'll see you next week.
Good night, everyone.
Good
Thank you,
night.
Sue.
Thank you.
Thank you.
All right.
Goodbye.